Welcome everyone to our session on the fundamentals of thermal radiation. Today we are going to trace the fascinating journey of radiative energy, moving all the way from its underlying microscopic physical phenomena up to the evaluation of three-dimensional radiative flux. Over the course of this lecture, we will demystify these concepts and build a robust framework for analyzing radiative heat transfer in real-world systems. Let's begin by outlining what we aim to master today. Before we dive into the physics, let's establish our roadmap with 4 core learning objectives. First, under Objective 1, we will define the physical mechanisms of thermal radiation, establishing its nature as a pure electromagnetic wave phenomenon. Second, we will analyze spectral distribution, which means we'll look at how emitted energy is distributed across different wavelengths and how temperature alters this distribution. Third, we will evaluate real versus blackbody surfaces. This is critical because it teaches us to contrast ideal, perfect radiators with the non-ideal, real-world materials we encounter in engineering practice. Finally, under Objective 4, we will learn how to quantify directional flux. This will give you the mathematical tools to calculate three-dimensional radiative intensity and determine net heat exchange. By the end of this session, you'll view everyday thermal phenomena through a precise, analytical lens. Let's begin by contrasting radiation with conduction and convection. The single most defining characteristic of radiative heat transfer is its total independence from a supporting material medium. If you look at the left half of the slide depicting a vacuum chamber, you see a hot object suspended in a perfect vacuum. Even without a single molecule of air to conduct or convect heat away, that hot object will still cool down until it reaches thermal equilibrium with its surroundings. This is because it radiates energy away in the form of electromagnetic waves. Now direct your attention to the right half of the slide, labeled the cold medium. Here, we see a person standing near a fire. Notice the temperatures. The person is at 30 degrees Celsius, the fire is at 900, and the intervening air is a chilly 5 degrees. Radiative transfer occurs directly between the fire and the person. The energy doesn't need to heat the intervening cold air to warm you up. It travels right through it. This independence makes radiation a dominant force in high-temperature applications and space environments. To truly understand thermal radiation, we have to pinpoint exactly where it lives on the broader electromagnetic spectrum. If you look at the top horizontal timeline, you'll see the entire spectrum, spanning from cosmic rays all the way to massive electrical power waves. Thermal radiation occupies a specific intermediate band highlighted in pink, stretching from 0.1 to 100 micrometers. If we zoom into that band using the lower diagram, we can break it down into 3 crucial subregions. On the left is the ultraviolet region, spanning from 0.01 to 0.40 micrometers. In the middle is the visible light region, a narrow window from 0.40 to 0.76 micrometers. To the right is the vast infrared region, extending from 0.76 up to 100 micrometers. Keep 3 key facts in mind. First, absolutely everything with a thermodynamic temperature above absolute zero emits thermal radiation. Second, solar radiation spans 0.3 to 3 micrometers, meaning almost half of the sun's energy arrives as visible light. Third, objects at room temperature emit entirely within the invisible infrared spectrum, which explains why we need specialized thermal imaging cameras to see them. When we model radiation in engineering, we must distinguish between whether it originates from deep within a substance or strictly at its boundary. This brings us to the distinction between volume phenomena and surface phenomena. Look at the top diagram, which represents a volumetric phenomenon. In gases, liquids, and certain semi-transparent solids, radiation is emitted and absorbed continuously throughout the entire volume of the material. Molecules deep inside the cloud are actively contributing to the total energy exit. Now look at the bottom diagram, illustrating a surface phenomenon. For opaque solids, such as metals or thick ceramics, any radiation originating from the interior atoms is immediately reabsorbed by neighboring atoms before it can escape. Therefore, the interior radiation never gets out. Because of this, engineering models treat emission from opaque solids strictly as a two-dimensional surface boundary condition. For the majority of solid body mechanical engineering problems, we will use this surface-based approach. To evaluate how efficiently a real object radiates energy, we require an idealized benchmark. In thermodynamics, that benchmark is called a blackbody. Let's compare them using the diagrams on this slide. On the left, we see a real body. Notice that its emission profile, represented by the pink envelope, is highly irregular and directionally dependent. Real surfaces are imperfect. They emit less than the theoretical maximum possible energy. On the right, we see the ideal blackbody. Its emission profile is a perfect, uniform hemisphere. A blackbody is a perfect emitter and a perfect absorber. It is a diffuse emitter, meaning it emits energy uniformly in all directions regardless of the angle. and it absorbs all incident radiation regardless of wavelength. Since a perfect blackbody doesn't exist naturally, how do we study it? Look at the bottom diagram. We can experimentally approximate blackbody behavior using a large, heated isothermal cavity featuring a tiny opening. Any ray entering that small opening undergoes infinite internal reflections and absorption, making the small opening behave like a perfect blackbody surface. This brings us to one of the most celebrated and fundamental equations in heat transfer, prominently featured right in the center of this slide. This central formula defines the Stefan-Boltzmann law for total blackbody emissive power. Let's break down what this equation represents by examining the structural callouts surrounding it. On the left side, the term defines the total emissive power, measured in watts per square meter. This is the total rate of radiation energy emitted per unit time, per unit surface area, across all wavelengths. Moving to the right side of the equal sign, the first term represents the Stefan-Boltzmann constant, a precise physical constant valued at 5.67 times 10 to the minus 8th watts per square meter Kelvin to the 4th power. Finally, the highlighted pink term defines the absolute thermodynamic temperature, which is raised to the 4th power. The core takeaway here is momentous. Total emission scales to the 4th power of absolute temperature. This means if you double an object's temperature, its radiative energy output increases by a factor of 16. This equation represents the absolute maximum thermal radiation a surface can possibly emit at any given temperature. While the Stefan-Boltzmann law gives us the total power across all wavelengths, we must also examine how that energy is distributed spectrally. This graph plots blackbody emissive power on the vertical axis against wavelength on the horizontal axis for temperatures ranging from 100 Kelvin up to 5800 Kelvin. Let's analyze the three core dynamics listed on the right. First, look at any single curve. Notice that emission is a continuous, smooth function of wavelength. It starts low at short wavelengths, climbs to a peak, and gradually decays at longer wavelengths. Second, observe what happens as temperature increases. As we move from the lower curves to the higher ones, the total emission increases drastically, and the peaks shoot upward. The area under each curve represents the total power, which grows rapidly due to that temperature to the 4th relationship we just discussed. Third, look at the dashed pink line cutting diagonally across the curves. This line traces the locus of maximum power and defines Wien's displacement law. Notice the annotation on the graph. The equation pointing to the dashed line defines Wien's displacement law, stating that the product of the peak wavelength and the absolute temperature is equal to a constant value of 2897.8 micrometer Kelvin. Consequently, as a body gets hotter, its peak emission shifts to shorter wavelengths. This is why a heating element first glows a dull red, then bright orange, and eventually turns white-hot as it approaches solar temperatures. Now that we understand both spectral distribution and total power, let's look at how they connect mathematically. The graph on the left shows a single spectral emission curve. The boundary line represents the spectral emissive power at a specific wavelength and temperature, while the entire shaded pink area underneath represents the total emissive power. To calculate that total area mathematically, we look to the right side of the slide. The primary equation centered on the right defines the mathematical integration of the spectral emissive power over all possible wavelengths from 0 to infinity. By executing this calculus integration, the spectral expression collapses beautifully back into the Stefan-Boltzmann law that we saw earlier. In short, this slide reinforces that total radiative energy is simply the sum of its parts. If you know how an object radiates at every individual wavelength, you can integrate that performance across the entire electromagnetic canvas to find the total heat flux leaving the surface. In practical engineering design, we rarely need to integrate from 0 to infinity. Instead, we often need to isolate a specific band of wavelengths. For example, if you are designing a greenhouse or a solar panel, you need to know exactly how much energy sits strictly within the visible light spectrum. If you look at the graph, the pink region highlights a targeted band between a first discrete wavelength and a second discrete wavelength. To find the energy in this band without performing messy integration every time, we use the blackbody radiation function, denoted by the symbol positioned in the section header. Look at the equation located at the bottom of the slide. This mathematical expression defines the band fraction calculation. It states that the fraction of radiation emitted between two specific wavelengths is equal to the blackbody function evaluated from 0 to the upper wavelength, minus the function evaluated from 0 to the lower wavelength. Engineers compile these fractions into standard, readily accessible tables. By looking up these tabulated values, you can instantly isolate any desired wavelength band with simple subtraction. Up until now, we've treated radiation as a hemispherical total. However, radiation is inherently directional. It shoots out into three-dimensional space. To handle this mathematically, we must transition from two-dimensional geometry to three-dimensional geometry. Let's look at the two analogies on this slide. On the left, we have a flat, two-dimensional plane angle, represented by a pizza slice. A plane angle is measured in radians and is defined by the arc length divided by the radius. It maps out a slice of a flat circle. On the right, we scale up to a three-dimensional solid angle, represented by a watermelon wedge. Instead of a flat arc, a solid angle measures a three-dimensional volume sweeping outward from a center point into a surface area on a sphere. It is measured in steradians. The solid angle is defined as the outer surface area divided by the radius squared. Now look at the highlighted box centered at the bottom. The equation on the left of this callout defines the differential solid angle in spherical coordinates, accounting for both the zenith angle and the azimuthal angle. The statement on the right of the box notes a vital geometric truth. A complete hemisphere contains exactly 2 pi steradians. Mastering this three-dimensional angular framework is what allows us to track directional heat rays precisely. Equipped with the concept of solid angles, we can now define the core directional vector of radiative heat transfer, radiation intensity. Let's analyze the spatial diagram on the left. We have a differential emitting surface area sitting at the origin of a three-dimensional coordinate system. It shoots a beam of radiative energy outward through a pink cone. This cone is positioned at a zenith angle measured from the vertical axis, and an azimuthal angle measured around the base plane. The arrow extending out of the cone represents our directional intensity vector. Now let's look at the text boxes on the right to see how this is defined. The top definition box states that radiation intensity is the rate of energy emitted in a specific direction, per unit area normal to that direction, per unit solid angle. Read the lower text box carefully. Why projected area? When you look at a flat surface from an angle, the surface appears smaller or foreshortened. Intensity accounts for this geometric foreshortening. If you look at the very end of the text inside that lower callout box, you'll see a small mathematical term. This specific term defines the geometric foreshortening adjustment factor, which uses a trigonometric cosine function to scale the area based on the viewing angle. Now let's connect directional intensity back to the total energy flux, leaving a flat surface. The diagram on the left shows our differential surface area at the center, surrounded by a wireframe hemisphere capturing every single directional intensity vector shooting outward into space. To find the total emissive power, we must perform a spatial integration. The equation located in the middle right of the slide defines this hemispherical surface integration. It is a double integral that sums up the directional radiation intensity across all azimuthal angles from 0 to 2 pi, and all zenith angles from 0 to pi over 2, while incorporating our geometric foreshortening factors. Performing this double integration for complex, irregular surfaces can be incredibly difficult. However, look at the highlighted pink box running along the bottom. For an ideal diffuse surface, the intensity is entirely independent of direction. It is constant. Because it's a constant, it can be pulled out of the integral. As a result, the complex three-dimensional integral collapses into a beautifully simple, linear relation. The two equations inside this bottom callout box define this collapsed relationship, stating that for any diffuse surface, the total emissive power is simply pi multiplied by the radiation intensity. For a blackbody, the total blackbody emissive power is equal to pi multiplied by the blackbody intensity. This elegant simplification is used extensively in thermal modeling. As we move closer to setting up engineering energy balances, we must carefully categorize the different ways radiation interacts with the surface. There are 3 distinct modes of radiative flux, neatly organized in this table. In the first column, we have emissive power. As shown by the upward-pointing arrows in the diagram, this represents the total rate of radiation energy generated and emitted directly by the surface per unit area due to its own thermal energy. In the second column, we have irradiation. Notice that the arrows in the diagram are pointing downward. Irradiation represents the total rate of external radiation incident upon a surface from all directions in the surrounding environment. This is energy arriving at the surface. In the third column, we have radiosity. Look closely at the diagram. It includes both a wave originating from the surface and a wave bouncing off of it. Radiosity represents the total radiation energy streaming away from a surface, regardless of its original origin. It combines the energy the surface creates on its own with the energy it reflects from its surroundings. Differentiating between what is emitted, what arrives, and what leaves is the key to avoiding errors in heat transfer calculations. Let's synthesize those 3 modes into a single, unified visual architecture. This diagram layout maps out exactly how energy balances at a solid boundary. Trace the gray arrows on the left. We have incoming irradiation arriving at the surface. A portion of that irradiation is absorbed, while another portion is reflected back upward, creating the reflected irradiation arrow. Now look at the right side. The surface is also generating its own internal thermal energy, which exits upward as emissive power. When we look at what is completely leaving the surface traveling upward, we see the thick, prominent pink arrow labeled radiosity. Right beneath this diagram, we find our structural equation. This mathematical statement defines the total radiosity, leaving a surface as the direct sum of its generated emissive power and its reflected irradiation. Now read the call-out box at the very bottom. For an ideal blackbody, remember that it is a perfect absorber, meaning its absorption is 100% and its reflection is 0. Because reflection drops to 0, the equation simplifies perfectly. Radiosity precisely equals the blackbody emissive power. For a blackbody, every bit of radiation leaving the surface originated entirely from deep within the body itself. For real surfaces, we must always account for the reflected component. To tie our entire mathematical framework together, this slide provides a comprehensive summary mapping. It contrasts individual spectral quantities against their total integrated counterparts across all 4 core properties: intensity, emissive power, irradiation, and radiosity. Look at the left column of the table. These terms define the spectral quantities at a single, discrete wavelength. They are localized values. Now look at the right column of the table. The expressions structured inside this right-hand column define the total thermodynamic properties, showing how each total property is computed as a definite calculus integral of its spectral counterpart across the entire wavelength range from 0 to infinity. If you glance at the graph on the bottom left, it visually illustrates this exact relationship for intensity, where a thin slice represents the spectral intensity at a specific wavelength, and the total integrated area equals the total intensity vector. The takeaway message in the bottom right text box summarizes this perfectly. Every total thermodynamic property is the integral of its spectral counterpart across the electromagnetic canvas. To truly understand the total energy of a system, we must account for every wavelength and every direction simultaneously. As we wrap up our session, let's consolidate our core foundational pillars into 3 key takeaways. First, remember the distinction between spectral versus total quantities. Radiative properties are highly wavelength dependent. To find the total flux, we must integrate these spectral intensities across the entire electromagnetic spectrum, transitioning from localized spectral values to total integrated properties like emissive power, irradiation, and radiosity. Second, master the rules of directional and spatial integration. Radiation is a directional vector, not a simple scalar. Calculating surface flux requires integrating intensity over a 3-dimensional hemispherical space. We must use a projected area term to mathematically account for geometric foreshortening, and we can leverage diffuse surface models to provide uniform intensity simplifications. Third, always sketch out your radiative flux architecture. Understanding the balance of energy leaving a surface is critical for thermal analysis. Always break it down. Emissive power is generated and emitted. Irradiation arrives from the environment, and radiosity is the total energy leaving the surface, which synthesizes emission and reflection into a single exiting stream. For an ideal blackbody, this architecture simplifies perfectly, because reflection is 0. That concludes our fundamental look at thermal radiation. If you look at the top left of this final slide, you'll find my contact email address for any follow-up questions or research discussions regarding these heat transfer models. Thank you all for your time, your focus, and your excellent engagement today. I look forward to seeing you in our next session.